Thank you, everyone. Welcome. This is the third talk in the series of the expert talk. Thank you for being here. This talk is titled as Automated Synthesis Towards the Holy Grail of Programming. We have Professor Supratik Chakraborty from IIT Bombay. Thank you so much for your time, Professor Chakraborty. I'll go with a very brief introduction of Professor Chakraborty, which is a little bit unnecessary. He is a very well-known name in the computing community. Dr. Chakraborty, he's a JB Scholar of 1989, is the Bajaj Group Chair Professor at the Department of Computer Science and Engineering of IIT Bombay. He is also the principal investigator of the Center of Formal Design and Verification of Software. He has won the Intellectual Property Award at Fujitsu Laboratories in 1999, the Indian National Academy of Engineering Young Engineer Award in 2005, the IBM Faculty Award in 2007, and many such prestigious awards. He had his BTech from IIT Kharagpur in 1993. He was awarded the President of India Gold Medal for the best academic performance among all graduating students of all disciplines. He had his master's and doctorate from Stanford University in 1995 and 1998. He worked as a member of research staff at the Fujitsu Laboratories of America for a year before joining as a faculty at IIT Bombay. His interest lies in constraint counting, sampling, scalable formal verification of software, hardware and intelligent systems, automated synthesis of programs and circuits, automated reasoning, and automated theory in general, logic and finite model theory. He's a fellow of Indian National Academy of Engineering. He's a distinguished member of ACM and a member of the Council of ACM India. He was a member of the Technical Advisory Board of Microsoft Research India. He was a member of the Science and Engineering Research Board of the Government of India. He is a research advisor of TCS. He has co-authored many referred conference papers and journal articles, which are available on his website. Thank you so much, Professor Chakraborty, for being here today.
Thank you, Arghya, for the kind introduction. And thank you, everybody, for joining this session. So depending on which part of the world you are in, good morning or good evening. And I must first of all thank, the Jagadis Bose Scholars Professional Development Forum for actually undertaking this initiative. I mean, not only for my talk, but I have been silently, watching and seeing the programs that are being conducted. I think it's an excellent initiative. It requires, some amount of groundwork to be done, and I'm really glad that, Arghya and the other organizers of these events are finding time to put into that. Thank you so much. I think this is an excellent way to actually further the professional development of all of us.
Thank you so much, Professor Chakraborty.
Yeah, it's an excellent initiative. And it's also a way to connect to so many people, seniors, juniors, who are part of the JB family. So without much ado, what I'll do is I'll get going with my talk. So I'll share my screen.
Yeah, let me stop sharing and please go ahead with your screen sharing.
So I'm going to switch between multiple screens. So in order to enable that to happen smoothly, I'll just share my desktop itself. Yeah, so what's this? Okay, is my screen visible?
Yep, I can see your screen.
Okay, great. So what I'm going to talk about today is, automated synthesis And this is indeed the holy grail of programming, as different computer scientists have sort of visualized what programming's aim should be. And what I'm going to talk about today is just motivating the problem, what automated synthesis is, trying to give some specific applications, why this is interesting, and if we can really solve this problem, several very interesting consequences will fall out of it. And then, given that this is a very diverse audience, and given that we do not have too much time, I would rather spend time in the interaction, in the discussion. So I'm going to talk about briefly about something that we have been doing. I'm going to give a simple demonstration of, what a good automated synthesis tool is capable of doing. Of course, this demonstration is going to be a very simple demonstration. The larger problem still remains unsolved. And then I'm going to end with some open issues in this area. So I must also acknowledge that various parts of this talk are taken from a tutorial that we gave at the AAAI conference this year, around a month back. So several slides here are taken with generous help from Kuldeep Meel from National University of Singapore, from Akshay, my colleague at IIT Bombay, and from Priyanka Golia and Shubhajit Roy, who are at IIT Kanpur. Priyanka is also affiliated to National University of Singapore. Okay, so Arghya, I roughly have 40 minutes, 45 minutes for the talk. Is that the plan? Arghya?
I think the total time is 2 hours, but I think you prefer to have like 45 minutes for the
talk. Yeah, I'd like to answer questions and sort of maybe go more into the interactive part. Okay, so let's start. So what is this all about? What is automated synthesis all about? Suppose you're sitting in your office and somebody asked you to design a system which, let us say, takes two inputs, x1 and x2, and gives an output y. And you're wishing that you could have a system which, behaves like what it is supposed to behave. But then what does it mean to say that what is it supposed to behave? So you have to give a specification of what the system should do. So you could give a specification by examples. Actually, this is a very natural, intuitive thing, saying that, well, okay, here are some examples of what I would like the system to do. So for example, if x1 is 20 and x2 is 3, I would like the output to be 20. And if x1 is 2 and x2 is 9, I would like the output to be 10. And you could give a list of such things, a finite small set of such things. And you could say, well, this is roughly what I want my system to do. This is my, very high level, very, example driven specification. Alternatively, I could also be a bit more formal about it and a bit more comprehensive about it. And I could write a logical formula saying, well, I want x1 and x2 to be numbers input to the system, y to be a number output for the system. And here is a formula that I would like to be satisfied, based on whatever y is generated by the system given inputs x1 and x2. So whatever system you design over here, this formula should be satisfied between y and x1 and x2. Now, one thing that you note when you look at this formula is that it is not directly giving you y as a function of x1 and x2. Instead, it's specifying some relation between y and x1 and x2. And the job of synthesis is, of course, to figure out what function of x1 and x2 can you assign to y such that this is satisfied. In a more ideal world, you could also give a specification in natural language. So you could say that, well, I want y to be the maximum of x1 and x2. But if both x1 and x2 are less than 10, then I want the output y to be just 10. Okay. So there are different ways in which you could, and these are not the only ways, there are other formalisms by which you could actually specify that I want to design a program, I want a program or I want a circuit which takes two inputs, gives an output, and this is roughly what the circuit should do. Okay, So what do you do? So you spend some time thinking about it, and maybe you are starting from this logical relation, specifying the relation between the inputs and the outputs. And then you say, okay, fine. I mean, here is a program which looks like is going to satisfy this specification. Okay. So whatever, you're doing some maximum, you're checking some less than 10, otherwise you're assigning to 10. So whatever, this is some program you have written. No guarantees that this program is correct, but you've thought about it for some time, looked at the specification for some time, and this is what you've come up with. But then your colleague comes up and says that, well, I mean, looks like, for some inputs and outputs that I give, it is matching. But how do you know that this program is going to do exactly what the specification asked it to do for all possible values of the inputs? So this is an interesting question, because I mean, clearly you can't possibly give every possible input and check, whether the specification is satisfied. So, the question is, maybe whatever you and your colleague have a conversation, you look at the program, use some techniques to reason about the program, and maybe you come up with a proof saying that, okay, it does look like that this program satisfies this logical relation. Now, what happens is the next day at work, somebody tells you that, well, you have to design a system which looks somewhat similar to the earlier system. It takes in two inputs, x1 and x2, gives an output y. And the specification, in any of the formalisms that you had looked at earlier, is actually slightly different from what it was earlier. And here I have highlighted in red what is the difference. So, for 20 and 3 earlier, it was outputting 20, now it should output 30. For 2 and 9 earlier, it was outputting 10, now it should output 12. But for 5 and 30, whatever it was outputting earlier, it should output the same thing. And similarly, a list of input-output examples. If you look at the logical relation, maybe this is the difference. There is an x1 plus 10 over here. And if you look at the specification in natural language, it looks, slightly more convoluted. We are saying that, output y as x2 if it is at least 10 more than x1, otherwise output x1 plus 10. Natural language, of course, has all kinds of connotations. And so now what you have to do, so it looks like that the specification is kind of similar to what the earlier specification was, but it's not the same. So again, you'll have to spend some time, and then you have to look at once again, the logical specification hard for some time. You take a hard look at it for some time, and then you say, okay, now it looks like I can come up with a simpler program. It just looks like it is max of x1 plus 10 and x2. But then your colleague comes up and says, how are you sure that this is correct as well? I mean, last time we had some, we needed to do some reasoning to convince that the last program was correct. But now, how do you know that this program is doing the right thing for all possible values of the inputs? And at this point, you start wondering that, well, okay, if people are going to give specifications and ask you to write a program or equivalently design a circuit that sort of implements that specification, I mean, doing this process every time, here you might have gotten lucky and come up with 2 correct programs, but every time to sort of think about, what the program should be starting from a specification, and then to think about all possible inputs that you could give to the program, this is going to be tedious. So you ask that, well, wish I had an algorithm that could help me. So I could give these kinds of specifications to the algorithm, and the algorithm would take in these specifications, and it would give me the program or the circuit, whatever I want to synthesize, whatever I want to design, and it would also give me a guarantee that it's provably correct. So if you had such an algorithm, then of course, the first day, whoever gave you the specifications, you could feed these specifications to this algorithm, and you will get a provably correct system. You don't need to rack your brains further about why that system is exactly doing what the specification asks it to do. And if somebody changes the specification the next day, fine. I mean, you just feed that to the same synthesis algorithm, and it outputs another system, which is once again provably correct. So this is the beauty of having automated synthesis, is that your requirements for what you want to design can keep changing. It can change drastically. It can change, in a modular way. It can change in small parts. But then if you had a synthesis algorithm which is able to digest the specification and sort of output a program along with the proof that it is correct, it implements that specification, life would really be so simple, right? And here I have given some very simple examples. I want a program with just, crunches two numbers and outputs another number. But these could be many, many more such examples, and I'm going to talk about a lot of such examples, in the coming part of the talk. But that's what we want to focus on. And in particular, you would notice that, if I give a specification like this, just by listing out a few examples, or I give it in natural language, then to find out an unambiguous meaning for that is kind of difficult. And of course, I mean, I'll talk about techniques where you can actually start from here and come up with an algorithm and come up with a system. You can have synthesis algorithms which will give a system starting from, specification by examples. Natural language, you can parse the language, you can come up with a formal representation of what is being said in that natural language, and then you can try to synthesize from there. But what we're going to focus on in this talk is probably, one of the simplest ways of specifying what a program should do in a very rigorous and unambiguous way is just by writing out a logical formula. So this is the part that I'm going to focus on, but I'm also going to touch on this other part at least, how do you synthesize something from a set of examples. Okay, so that's what the primary focus of my talk today will be about, that we'll start from a logical relation, and I'll show you a demonstration how we can write such logical relations between inputs and outputs. And we press the button and out comes a program / circuit, whatever you want, along with the proof that it's actually implementing exactly what this is supposed to, or what the specification wants you to synthesize. Okay. So are there any questions at this point about, at a high level, what is the problem we are trying to solve?
Just a quick interruption.
Yeah.
So everyone, so Professor Chakraborty encourages you to ask the questions online in an online fashion. So you can either raise your hand or, put the question in the chat as well. That'll be wonderful. It will be kind of a discussion. I have a question of myself.
Yeah, sure. So although, I mean, maybe I'll request one thing, because I may not be able to follow the chat while I'm speaking. So if somebody does raise a hand or post something on the chat, if you could alert me.
Absolutely. Absolutely.
Yeah. Please Absolutely. Go ahead with the question.
My question is, so this study focuses on given some equations like that, and sort of example like that, it will give you a relation, a logical relation, and it will not try to get a linear algebra types equation, right? So
it doesn't have to be linear algebra. In fact, the demonstration I'll show you that we are going to go nonlinear.
Okay.
It is just a relation between inputs and outputs in a specified logic. So here, of course, I have used Boolean combinations of linear inequalities, but it doesn't have to be that. This is just to illustrate.
So in other words, if I say this statement that given a set of relationships of x1, x2, and y, our goal is not to find, it's not a curve fitting problem that we are chasing here. It's rather a Boolean relationship that we are trying to formulate.
Well, so that's a very good question. So as you can see from this picture, the data types here don't have to be Boolean, although, I'm going to focus mostly on the Boolean part for the remainder of this talk, just to keep things simple. But this, logic formula could be on integers, could be on reals, could be on floating point numbers. They don't have to be Boolean. And, your question about curve fitting is interesting, because what we do in curve fitting is, so suppose I give you a logical relation like this, what I'm showing on my screen. So you will have to generate some points from this logical relation, and then you will maybe try to fit a curve on those, right? So you'll say that, okay, if x1 is 20 and x2 is 3, then y is 20 satisfies this, so I get a point like this. So if I give you a logical relation, and if you're trying to do curve fitting, you'll basically have to generate sufficiently large set of points, and then you'll try to fit a curve over there. But you know, a relation like this, I mean, even if I say that x1, x2, and y are 64-bit numbers, the total number of possible combinations here would be 2 raised to 64 into 2 raised to 64. That is an astronomical number. You cannot possibly generate all the points and then try to fit a curve. So you'll be just generating some of the points and trying to fit a curve. And then the question remains, I mean, your colleague can come back and ask that, okay, for those points, I can see your whatever system you've synthesized is doing the right thing. But does it do the right thing for the points that you have not sampled from this relation? Okay. And that's what we want to move towards. You know, even when we start off with specification by examples, we actually try to infer a relation from there. And then from that relation, we try to synthesize the system. Because whatever we are trying to synthesize, we want it to be correct with respect to a specification that talks about all inputs. Okay. So the curve fitting would work if you could actually generate all possible inputs and correspondingly all possible outputs. Actually, you know, I mean, here in this particular example, y is uniquely determined given x1 and x2, but in the demonstration I'll show you, I can just change the specification so that there may not be a unique y. For a given x1 and x2, there may be multiple values of y that satisfy the logical relation. And in that case, it's okay for your synthesis algorithm to come up with a program that generates some y that satisfies the specification. And you know, if you want to go more advanced, you can put quality metrics on the program or circuit that you're synthesizing, and you could say that, well, I want my circuit to synthesize a y which is the minimum possible, or I want to synthesize a y which is whatever closest to a prime number, things like this, right?
I see.
So a relational specification like this actually does not always uniquely specify the output in terms of the inputs. It just gives a relation between allowed outputs and the given input.
I see.
So
thanks for the clarification.
Yeah, so curve fitting would work only if you had, you know, sort of kind of unique outputs or maybe small values of outputs for every input combination. And more importantly, if you have the number of samples that you can generate, if that's a small manageable number. I mean, of course, you know, with big data techniques, you can deal with large numbers. But what I'm saying is the numbers we're talking about, if I have to generate every 64-bit integer and every 64-bit integer for x1 and x2, that number would be astronomically large, even for modern big data techniques, right?
We have a next question from Siddhartha Sengupta. I'm going to read out the question.
Please.
I understand this is a very simplified explanation, not using example, any other typical controls like if, then, or repeat until, etc. How does this diverge from typical decision tree generation in this example? This is the question.
Oh, okay. Yeah. So, so decision trees are a special case of programs that you can synthesize through this. Once again, it comes back to the same thing, that if you're trying to design a decision tree from a given set of samples, then what you're trying to minimize is perhaps the error of the decision tree with respect to that set of samples. What we are talking about here is a logical specification which must be satisfied for all samples that satisfy the data types. So for example, if x1 and x2 are 64-bit integers or whatever 64-bit floating point numbers with some mantissa and some exponent, you know, precision, then we would like, I mean, even if you are trying to generate a decision tree, actually decision tree generation is a special case of automated synthesis. In the literature, most of the decision tree generation things come from a sample set. But even otherwise, if you're trying to generate a decision tree, that's just a special case of what automated synthesis can do. But that's a very good question, because what we will see is that the kinds of, at least in the demonstration, the kinds of programs / circuits that I'll show you can perhaps also be generated as decision trees, except that if you want to generate those as decision trees, your decision trees will become much larger than what we can generate. If we sort of keep this as a normal program or a normal circuit. So Siddhartha, does that answer your question? Maybe
yes, Supratik, but we will discuss later offline.
Yeah, sure. So maybe as I go ahead,
the first part of the question, I'm still waiting for that. You do not have any other control. For example, if then repeat until iteration loops, so things like that are not there here.
Okay, so I will.
It's not a full-scale programming structure.
No, you can have repeat until things also. I will talk about it very briefly, but not in the demonstration. So I have a couple of slides on that as well. So you can have some looping structures as well. I mean, that problem is of course much harder, but you can have some looping structures. So let me come to that, and then maybe we will look at that. Okay. Okay, great. So interactions are always very welcome. So so the first point that I want to emphasize is that this problem cannot be too easy to solve, even if you say that you are just looking at no loops, loop-free programs, and even if you say that I'm going to limit my data types to finite data types. So let us say I'm saying that x, y1 and y2. So here it's a slightly different setting. There is one input x and there are two inputs y1 and y2, and I want to design a program or circuit. And what is the specification that this program should satisfy? So here, I'm even restricting myself to saying that these are not necessarily all possible integers, but let us say they are n-bit integers where n is some number, maybe 512 or 256, whatever. So these are all integers of that much bit width. So there are definitely finitely many values that you can take. And then the specification that I want the system to satisfy is that the input is the product of the two outputs. If I flip these arrows, it's a very simple system. If I say y1 and y2 are inputs and x is the output, and I want x to be the product of y1 and y2, what's the big deal? Just put a multiplier there, just a multiplication operation. But here x is the input and y1 and y2 are the outputs. And I want to say that given an x, I want you to generate y1 and y2 such that the input x is the product of y1 and y2. And I don't want y1 to be 1 and I don't want y2 to be 1. So this, subscript of n just here means that this is n-bit multiplication and this is an n-bit unsigned integer, let us say 1, and that's an n-bit unsigned integer 1. So I now want you to synthesize y1 and y2 as functions of x, which satisfies the specification. And you can look at the specification and you can see that, well, I mean, this specification is not very hard to write down, right? I mean, even if I asked you to write down in terms of the individual bits, it would not be too big. I mean, if this is an n-bit number and this is an n-bit number, this multiplication would just be order n squared at most. And these are, of course, order n. So the specification is, certainly no larger than order n squared, even if I were to write it down in terms of individual bits. So the specification is not large. However, what am I asking for the system to do here? I'm asking for the system to factorize x in a non-trivial way, right? Given x, I want it to give me factors y1 and y2, which are non-trivial. I don't want any one of them to be 1, such that x is equal to y1 times y2. And you see here that this is an example where the answer may not be unique. So for example, if I give x as 32, I can give 4 and 8, or I can give 2 and 60. So the answer may not be unique, but that's what I want my specification to do. And I'm sure, everybody in the audience would be aware that if we can solve this problem, basically if we can factorize efficiently, then we can break modern crypto systems. Okay, so this problem is not going to be easy to solve. And there's another important point to note here is that if I give x as a prime number, then of course there are no non-trivial factors of a prime number. So for some inputs, it may not be possible to come up with any outputs y1 and y2 such that the specification is satisfied. And if that is the case, that for a given input, there is no way to come up with any outputs such that the specification is satisfied, we will say, okay, I mean, these are not interesting cases because in any case, no matter what output you generate, the specification can't be satisfied. But we will be concerned about the cases where for a given input, there is some way to assign values to the outputs such that the specification is satisfied. And in the crypto context, we know that the kinds of factorization problems that are interesting are where x is the product of two large primes, right? If x is the product of two large primes, then and if I ask for non-trivial factors, you are actually going to get the two large primes only at the output, right? y1 may be the first prime, y2 the second prime, or vice versa, but the only way to non-trivially factor a product of two large primes is to get back those two large primes. And if we can do this efficiently, then we have broken modern crypto systems. So, and as of today, as I speak, there are no known efficient techniques, whether as a circuit or as a program, which can solve this problem. But note that this comes from such a simple specification. It's very easy to specify the problem. It's extremely hard to solve this problem. Okay, and this kind of I hope it illustrates the nature of the problem, that specifications are often easier to state. Designing a function that satisfies the specification is often significantly harder. And I'll show you some fundamental computational bottlenecks that lie along this en route as we try to solve this problem. Okay. Now, when we are talking about synthesis, as Siddhartha just mentioned, there are two very broad categories of synthesis problems that we talk about. One is called reactive synthesis, where the system and the environment are in continuous temporal interaction. So a controller controlling a plant is probably this kind of a system, where the controller is giving inputs to the plant and the plant is responding to those inputs. And again, the controller is giving back inputs to the plant. And in such cases, the specification often talks about an infinite sequence of inputs and outputs, rather than just saying, if the input is this, then the output should be that. Right? For example, if let us say you're talking about a controller, which is in the autopilot software for a modern aircraft, it's in continuous interaction as long as the plane is flying with all kinds of sensors that are measuring all kinds of things, velocity, air pressure, airflow, all kinds of things. And at specific periods, at specific intervals of time, those sensor inputs are coming. The controller is taking decisions, sending signals to the actuators. The actuators are, maybe whatever, changing the fuel injection rate, changing the, tilt of the ailerons, whatever. And again, the sensors are giving back input. So this is a continuous interaction between the system and its environment. And when we talk about such specifications, we may want to say that at no point of time, if the velocity is greater than something, then the brakes on the wing should come up. So we are talking about an infinite sequence of inputs, saying at every point of time. It's not just once you do it and then you're done with it. At every point of time, there is some relation between the inputs and the outputs, and such specifications are very commonly expressed using special logics like temporal logics, or equivalently using automata over infinite words. And examples of such systems are an operating system, a network switch, a nuclear plant controller. Now, I'm not going to focus on this for most part of this talk. I will show some connections to it, but I'm not going to focus on this for most part of this talk. What I'm going to focus on is what is called functional synthesis. And in functional synthesis, we are really concerned about outputs at a particular point of time in response to inputs at that point of time. So there is no dependence on past history. It turns out that a functional synthesis is a sub-problem in reactive synthesis. If you want to solve reactive synthesis, you can reduce it along with some other steps to the functional synthesis problem. And so here the proposition, the specification talks about just the current input and the current output. And so you have logics like propositional logic, bit vector logic, first order logic. You probably do not have temporal operators. And these kinds of things are often used for program synthesis, where you just want to transform an input to an output, some arithmetic or numerical computation. As I said, the next state logic of reactive controllers really boils down to functional synthesis. So that will be mostly the focus of this talk. And to keep things simple, I'm only going to focus on Boolean inputs, outputs. As we go to richer data types, the problems also start becoming correspondingly harder. Okay. So here is for the functional synthesis problem in the specific context of Booleans. So the Boolean part is just, I have put in here to sort of keep the treatment simple. Whatever I'm going to say, at least on this slide for the definition of the problem, you can replace Boolean data types with other data types, that's fine. So you're given a formula on some input variables and some output variables. And this could be the formula for factorization, the formula for computing the maximum of some numbers, whatever other formula you have. You're given a Boolean relation between the inputs and the outputs. The relation does not tell you how to what functions of the inputs will suffice for the outputs. And what you're required to do is you're required to synthesize, because we are talking Booleans, so Boolean functions or Boolean programs. By a Boolean program, I mean a program that just deals with Boolean variables. One such function or program for each output such that the following condition holds. That for any given value of x, if there are values of y1 through ym that can make the specification true, then these functions, when substituted for y, will also make the specification true. Okay, so let's go over this statement once again. So for any given x, if there is some value for y1 to ym, I may not know what those values are, but if there is some value for y1 to ym that makes the specification true, if I plug in those values here, the specification becomes true for the given value of x. Then if I plug in the functions that I'm required to synthesize in place of y1 to ym, then that specification will also evaluate to true. Okay, so in the notation of logic, I'm saying that as long as there exists values for y1 to ym that render this formula true, if I substitute f1 through fm in place of y1 through ym over here, then also this formula will evaluate to true. And I want this to hold for every possible x. So really, that's what I want. Okay, for every possible x, if there is some way to assign values to y1 through ym that renders the specification true, then the specification is also rendered true when I substitute the synthesized functions or the synthesized programs in place of the y1 to ym variables. Okay, and in the literature, in the logic literature, such functions which have this property are also called Skolem functions for these variables in this formula. So, functional synthesis is also called the Skolem function synthesis problem. And this is regardless of whether your types are Boolean or not, you can have whatever data types. This is the Skolem functions arise in the context of first order logic. And this is a first order logic formula. And you can put in whatever data types you want for x and y's. What we are interested in is basically synthesizing Skolem functions for the outputs. The name Skolem comes from a famous logician mathematician, Thorab Skolem, who actually, so of course, has done seminal work in logic. But one of his contributions was to introduce these functions, which are known today as Skolem functions.
We have a question here, Professor.
Oh yes, please.
So on this slide 11, the question is from Professor Sengupta.
Yes.
Do you want to know the functional forms, or can they be black boxes?
We want to synthesize programs. So it is okay for F1 to FM to not be, for example, suppose I'm using, suppose this formula is expressed using linear algebra. So it is okay for F1 to FM to not be a linear algebra term, but I would like to get a program which computes these, because at the end of the day, I mean, think of this as a specification where these are your inputs and these are the outputs going to maybe a plant, a nuclear plant or a chemical reactor plant. You want to actually generate these outputs looking at these inputs. So I would like to have programs that compute F1x through Fmx given the values of x1 through xn. It is okay if those programs, my specification might have been in a linear algebra formula. It's okay if the programs are not restricting themselves to linear algebra, but they have to be programs, they have to take in the inputs and they have to generate the outputs, which I can plug in so that I know how to generate maybe these inputs to the plant such that my specification is satisfied. So I do want to know the functions as black boxes. So, since Siddhartha asked, let me also point out. So, the work of Thoralf Skolem actually says that for any first order logic formula, there always exists such functions. The question is, are those functions computable? Can they be computed by any program, by any Turing machine, by any circuit? It turns out that the answer is no. Although, for any first order logics, for any such first order logic formula, there always exists such functions. They may not be computable, in which case, that's a specification for which we really can't do much. I mean, we know that there is a way to generate the outputs, but the way to generate the output cannot be done by any program, by any Turing machine. But when these functions are computable, actually finding out what those functions are is a very, very difficult problem. And there are cases, as part of our work, we have shown that there are cases where we know that there are computable functions for F1 through Fm, but finding that program algorithmically is impossible. So as you go to the full generality of first order logic, there are all kinds of computability issues come in. Do these functions at all exist as computable functions? The answer is no in general. Even when they exist as computable functions, can we algorithmically synthesize programs to compute that functions? The answer to that also is no in general. Okay, so therefore, we can only reason about specific fragments of first order logic. We can only reason about restricted logics where we can actually algorithmically compute this. And what I'm going to talk today is, of course, the simplest case, Boolean, in which case, of course, we can compute. So we want the functions, we don't want them as black boxes. The black boxes always exist. Okay. So Siddhartha, did that answer your question?
Partially, we'll discuss later. There's
Okay.
another question in the, Arghya can read that out.
Oh, okay.
Yeah, so sorry. Yeah, there is another next question, which is from Shourish.
Sure.
So the question is, are there any limitations in the Skolem function, like the degree of the function or any range?
It's an excellent question. Excellent question. So, in fact, as I just mentioned, that these functions are not even computable in general. And indeed, you may find out that, yes, it is possible to compute that function, but the program that is computing that function is horribly complex, or you cannot even put an upper bound on the complexity on the running time of that program. So in practice, what we would really want is that we would like these functions to come from a very well-behaved class. I mean, we know that There may not be any functions from those well-behaved class that satisfy this property, but the useful instances of this problem are where these functions are coming from some well-behaved class, and there you can indeed put in, I mean, these functions. If you're talking about as polynomials, you can say I want to restrict the degree of the polynomial. If you're talking about linear constraints, you can say, okay, maybe there are so many disjunctions of linear constraints I will allow, piecewise linear, but so many pieces in that. So you can put in all of these restrictions. You may want to bound the running time of the program that you're generating. You may want to bound the size of the program, because these programs eventually may have to go on some embedded systems. So you may want to bound the power that the program consumes. So there are all kinds of quality metrics that you can put on these functions. Unfortunately, that area is wide open right now. That, I mean, we barely know a few things about how to compute these functions. I'm going to show you a few of those results. As you put quality metrics, that's really where the practical utility of this would be, it would really meet the practical usage where you want to put this. So in general, if you take a first order logic formula, you can't even compute these functions. Even if you know that you can compute these functions, you may not be able to put any restrictions on how complex the program is or what the running time of the program is. But indeed, we would like to do Skolem function synthesis where we control how complex or how large these functions are. So that's an excellent question. It's an open question. We actually do not have much idea about how to do quality controlled Skolem function synthesis. Okay. Shall I proceed or no?
Please. Thanks, Shoris, for asking the question. If you definitely feel free to ask any follow-up questions.
Yes, I think that's great. I mean, we are looking ahead several slides, but that's great, because I think my main purpose is to give an understanding of this problem and then a little bit about what we have been able to do. Okay, so there is one interesting thing, as I showed with the factorization example, that it may not be the case that for every x you can find a y. So if you ask, is this formula always true, that for every x there exists a y phi of xy, that may not be true. But still, this problem is interesting, because as long as there are some x's for which you can find a y, which satisfies the specification, you are interested in finding those y's as functions of those x's where actually there exists such a y. In the other cases, it's inconsequential. Okay. So this is kind of slightly putting it in a formal way. What I want to do now is I want to show you a few applications, and after that I want to show you a demo, and after that I want to talk about some of the technicalities of how some of these are solved. Okay. So the first application that I want to talk about, this is a very well studied application, is to synthesize programs for domain specific tasks. Okay, and for example, for data preparation in machine learning tasks, you want to synthesize R scripts for complex data wrangling tasks, and once again you can either try to specify what you want that script to do through a set of examples from which a logical specification is inferred, and from there you can try to synthesize these scripts. But this is actually a very, very practical line of work. You want to automatically synthesize scripts for data wrangling tasks. Data extraction, this is once again gaining a lot of traction in recent times. You want to synthesize SQL queries. Actually, I mean, as we move towards more and more data-oriented tasks, programmers often need to program in SQL queries inside their programs. And not every programmer is very proficient in SQL. They may be writing queries which are horribly inefficient. They're not at all optimized. So what we would like to do is to basically relieve programmers from this task of synthesizing optimized SQL queries. So synthesizing SQL queries and Python scripts, once again from examples of input and output tables. It's a very, very active line of work very interesting recent work is there in this. You can also do data visualization. So once again, you give small examples of data that you want to visualize, and there may be multiple ways to visualize the data. You can give some kind of specifications, quote unquote specifications, of what you want to see in your visualization, in the sense, what kinds of relations do you want to see in the visualization, and the visualization gets automatically synthesized. Once again, very interesting recent work. And you can also do it for machine learning pipelines. You can generate supervised learning pipelines through this. And here is something that perhaps a lot of you, maybe all of you, have already used. I mean, this is Microsoft's flash fill feature. So if you go to Microsoft Excel and then, actually I had a little video, but anyway, let me tell you, I'm sure most of you, let me see, since my screen is shared, yeah, I think that's the Microsoft video. Is my screen visible, Arghya?
Yes, we can see the demo. Yep.
Okay. No, this is not my demo. This is a video from Microsoft, but showing what the flash fill feature is. I'm sure a lot of you have already used it, but let's just see. It's a few seconds, so we'll see the magic that happens. So basically, here is a Excel sheet, and here are some last names, name and first name, and I guess I will have to share my sound. But anyway, I think even if the sound doesn't come, should be fine. So what happens is,
or say you have information in Excel that isn't.
So is the sound audible, Arghya?
Yeah, the sound is also audible, thankfully.
Okay, great. So just a few seconds, you have an Excel sheet and this is what you're trying to do.
Formatted the way you need it to be, such as this list of names. And going through the entire list manually to correct them is daunting. You'd think there'd be an easier, automated way to do this too. And you'd be right again. Type the first name the way you want it. Start to type the next name, and, as if by magic, Excel provides a preview of the names formatted the way you want. Press.
Okay, so yeah, let me come back to my presentation. So this is the flash fill feature of Excel, which it's almost, I guess, close to a decade now that it was introduced, and then it's now in the commercial, it's shipped along with commercial Excel. And this is once.
I have a question regarding Excel mostly, which is, wasn't this already a part of your the small functions that you can write? And obviously, this is not an integer type of function, so numerical function. This is a what you call it, the property sort of function.
The string processing function.
Yeah, string processing function. Wasn't this already a part of this? Like you just write equal to.
You really have to copy paste that in all the cells.
Yeah, so
you can just drag it down, I believe.
Yes.
No. So I think you have to write a formula. That's what you're talking about, right? Yep. Arghya? You have to write equal to some string function, this, that.
Yep.
Right? Yep. Of course, if you write that formula, then it computes according to that formula. But then you have given this column function. That formula is telling you from the inputs from the given columns how to compute the output column.
I see. Okay. Now I can relate to your first example of this talk, which is instead of giving that formula, if you just write the output that you want for
write a few examples. Yeah.
Can you write compute the formula?
And then the formula gets computed such that when you apply that formula. So in flash fill, what happens is you type in one or two rows like this, and it depending on the complexity of what you're doing. It can actually infer fairly complex Excel formulas. If you look at those formulas, sometimes they're fairly complex. But as you type in rows, it's trying to infer what is the logical relation you wanted between the inputs and the outputs. Right. So, for example, in this case, it's trying. you're typing in a string, so it knows that you're trying to do some string transformation, and it's trying to sort of, in some sense, do some intelligent guess about where did this come from. This came from here, maybe by capitalizing the first letter. And where did this come from? It came from here by capitalizing the first letter. So maybe in the next one also you want to do this. Maybe, I mean, this is just a conjectured or a candidate's column function. And it shows this over here. It says that I'm not really sure, but maybe this is what you want to do. And if you disagree, maybe, you pick a row where it's not exactly what it's telling you is not exactly what you wanted. And you write here what you want. And that is, one more example telling that why the logical relation that it had inferred from which it had synthesized a program is not correct. And then it will go and correct itself. It will say, okay, now I can see that's, maybe not, that row was not satisfying the logical relation I came up with. And you have provided an input which tells me what the logical relation should be. So I will use that to synthesize a new program.
Wow,
right?
wonderful.
So this is actually, I mean, it's a big commercial USP for Microsoft. I mean, because when you have large sheets, and most of the times you're actually doing string processing, which and it's not just string processing, it can actually do numerical processing, date processing, a whole bunch of things that it can do, right? I mean, of course, when there is money, Microsoft puts in a lot of effort into it, and it's really, I mean, if you haven't tried it out, maybe you can try it out. I mean, you can go to OpenOffice on the Microsoft's, the free version, and you can try it out there also. It almost feels like magic. That how did it know that this is exactly what you want to do? And then you can actually see the program that it generated. The program that it generated may not be as simple or as elegant as the program that you would write, the Excel formula that you would write. But that's not the point here, right? I mean, of course, that is a point if you care about the quality of the program, the readability of the program. But the point that Microsoft's flash fill is trying to say here is that you wanted to do some transformation, and this is a complex transformation, and you are not even familiar with this Excel programming language. You just give me a few examples, and I can synthesize these programs, show you what the output should be, and if you think they're okay, we can commit that, and that's the formula that will be synthesized for that column. If you think they're not okay, you tell me where they have gone wrong, and I will resynthesize it again. Okay.
I have a question regarding the resynthesizing part.
Yeah.
And that may be two different questions as well. Let me
Sure.
ask that.
Sure.
The first, so one thing is from the demo, another thing is from your example that we saw in the beginning of the
Sure.
presentation,
Sure.
where you showed us that given some examples, you are synthesizing a formula, or you were trying to automatically synthesize a formula. Given some changes in those relations, you are resynthesizing the formula. And
right.
here as well, one of the preliminary automated synthesis is done. If you're happy with that, it's done. If you're not, if you want some particular changes, you keep on doing those changes, and it keeps on resynthesizing based on your inputs. That's a really interesting thing for me. It's kind of working as a feedback from every sort of layer, if you think in a way of a deep learning terminology, as if from every layer it is kind of using as a feedback. Is it actually resynthesizing, or is it actually using a feedback?
No. So it is actually learning. So you're right. It is actually learning, and the way it is learning, of course, there are the way Microsoft's flash fill works, and there are papers written on it. But in general, given a set of data points, you can learn a function which maybe matches a large part of those data points. For example, this is what you would normally do if you're trying to synthesize a decision tree, let us say, right? You've given a set of data points and you synthesize a decision tree from those data points. Now, what you want to do is you want to apply the decision tree, the synthesized program, decision tree being one case of a synthesized program. And you want to find out what errors have happened. Now, when you find errors, do you go back and resynthesize another decision tree? I believe that's your question. So you don't go back and repeat the whole process all over again. You actually do a correction on this incrementally. You say that, okay, I've synthesized something, it is already matching a large part of it, but there are some places where it has gone into error. So I'll have to try to figure out the pattern or the generalization of the error. What is it that I have done wrong? And from there, I will have to try to fix or repair the function that I have synthesized, so that it now, is matching on the things that it gives an output that matches the things that it was earlier not matching. So I have just a couple of slides. This is actually a lot of technical work has been done on this. That how do you learn an initial function and then repair it incrementally as I show you where it is going wrong, rather than relearning it all over again.
So this incremental learning is much more difficult than learning all over again.
Incremental, so incremental repair, no. I mean, incremental repair, depending on the problem context, incremental repair can be much more effective. Actually, I'll show you some tools. My demo that I'm going to show you is based on incremental repair. Okay, so of course,
for example, incremental learning is not it's how it works. However, for decision trees, only one version of decision trees can do incremental. Most decision trees don't do incremental.
Yeah, so I think there is a slight difference between the incremental learning that we talk about in the machine learning literature and what we have over here. So, what we have over here is that there is some kind of a logical relation that we are trying to infer, and we're trying to synthesize from that. Okay, so it is not entirely data driven. I mean, from the data, we are trying to infer some kind of logical relation. And from that logical relation, we're trying to see where is that logical relation not, and that logical relation may or may not be a decision tree. That's some formula in some logic. And from that logical relation, we are trying to find out whatever we are synthesizing, which could be a decision tree, which could be an implementation of the synthesis from that logical relation. Is that doing the right thing? If it is not, then can I do a repair of it based on the logical relation? So it's in incremental learning, basically, at least, the standard framework for that. I mean, you learn something and then you give, more things to learn, and you're trying to sort of not change what you have learned earlier, but incrementally trying to change your learning model. But here you also have this specification, as I talked about, right? From the examples, I'm trying to infer a specification, and I'm trying to synthesize something which implements that specification. So it's not just the data.
Yeah, let's move ahead.
Okay, great. So flash fill I wanted to talk about, because this, I think a lot of you have already used it. There are actually very interesting applications of this for problem generation. I mean, in this online world, for 2 years almost, all schools and colleges were locked down, and also in the MOOC setting, which used to happen before the lockdown. You probably have 10,000 students in your class, and they're all distributed geographically all over the place, and they are all in internet touch with each other. How do you give a problem assignment such that you are relatively sure that copying is not going to work? So once again, we can actually you can specify parameters of a problem, and then you can synthesize these problems. For example, here, I'm just showing you one specific example, which comes from some paper not written by us, which is actually trying to synthesize a program that is doing geometric constructions. So it's saying that, at a very abstract level, I mean, there's a domain-specific language, of course. It's saying that there are 2 points, P1 and P2, and there is a line that you want to draw between P1 and P2, and you want to find a program that gets the midpoint of that line. And of course, these systems have a lot of axiomatic knowledge about Euclidean geometry, and the program that it's trying to synthesize from there. So the fact that you want the midpoint of a line between P1 and P2 is a logical formula. I mean, we may not know how to get the midpoint, but we know exactly what the formula is. What is the relation between the point I'm computing and the points that are given to me? And then this is the kind of program that may come out of it. Actually, this is what does come out. This is a simplified version of that from the work done by others. And this, if you recall and go back to your maybe 6th standard, 7th standard, or 8th standard geometry, this is exactly how you do. So you start from one end of the line, you draw a circle with a certain radius. Here the radius is the length of the line itself. And here you draw another circle from the other end of the line. And these two circles are going to intersect at 2 points, Q1 and Q2. And then you draw a line between Q1 and Q2 that intersects the line between Q1 and Q2. And that intersection point is R, and that's the midpoint. So this is the normal geometry construction that we all learned in our high school. But given sufficient axioms about Euclidean geometry to your system, and given this precise specification of what exactly do you want from P1 and P2, what is the point that you want to compute from P1 and P2, it is actually possible today to synthesize programs like this. Okay. Of course, if you talk about very complicated geometrical constructions, I don't think we are still there yet, but these are baby steps in that direction. This has also been used actually for feedback generation. So when we have introductory programming courses, introductory automata courses, and somebody does a mistake, right? So that mistake is kind of the input to my system, and its output should be the feedback. And my specification is that there's some relation between the input and the output, that the output should not be too verbose, the output should correlate exactly with what category of error the input has, and so on and so forth. And this has also been used in that context. Okay, so program synthesis, there are very many different ways of doing this. What I'm going to show you today is about this one particular method where we reduce it to, actually this is work done by my colleagues and collaborators at IIT Kanpur and National University of Singapore, where we reduce it to what is called quantified Boolean formula solving. And this is how it looks like. So for example, this could be my specification that I want to synthesize a function f of two arguments x1 and x2, such that whatever it returns is greater than equal to x1, greater than equal to x2, and it's either equal to x1 or equal to x2. And we can actually write it down in this formula form, that for every x1, x2, I want to get a y which satisfies this formula. And this can be done, basically if I synthesize y as a Skolem function of x1 and x2, I have actually synthesized this function f. And of course that Skolem function I would like to synthesize either as a circuit or as a program, so that I can actually compute that function. Okay. Now there is another application domain that I want to talk about. I talked about program synthesis, and all kinds of very interesting things can be done in the context of program synthesis. This is another area where actually a lot of very fascinating things can be done. So I'm talking about Conway's game of life as just a specific example. So many of you are probably already aware of this. It's a two-dimensional grid in which every cell is considered either live or dead. And then there are some rules. For example, if you're dead and if you have 3 live neighbors, then you become alive. And if you're live and if you have 2 or 3 live neighbors, then you continue to live. But if you have greater than 3 live neighbors, then you die, and so on and so forth. So this is sort of somehow meant to simulate, some life processes as they happen. But that's not our concern right now. And an interesting question about this is that, is there what is called a Garden of Eden configuration, which means that it's a configuration of the cells being live or dead, such that there is no configuration from which you can enter that configuration. So it's like a Garden of Eden which cannot be reached from anywhere. So it's a configuration which is kind of isolated. If you were to draw the reachability graph of this configuration is not reachable from any other configuration. And if there is no Garden of Eden, then we would like to say that, okay, then that means that every configuration is reachable from some other configuration. So given a configuration, what is the configuration from which I can reach it? So we want to give a witnessing function that defines the predecessor configuration. Okay, and this has a very storied history. People have applied all kinds of mathematical tools and techniques to try to solve this problem. It turns out that this can be solved as a scaling function synthesis problem, where you say that, this is just a binary grid, cells are either live or dead. So you can say that, you can basically give the entire 0-1 pattern in this entire grid as you're saying that that's the current configuration, and you want to know what is the previous configuration, such that you can go from the previous configuration to the current configuration. And how do we go from the previous configuration to the current configuration? These are the routes for that. Okay, so you can write this down as a formula, and then you are basically asking this question, that for every configuration, does there exist another configuration from which you can reach the configuration X? And if this formula is true, from every configuration you can reach another, for every configuration you can find a predecessor configuration, then the Garden of Eden does not exist. And if not, then the Garden of Eden exists. And of course, in this case, if you're answering that the Garden of Eden does not exist, then you would like to find these Y's, these predecessors, as functions of the current configuration. If you're saying that there's no unreachable configuration, then you would like to know for a given configuration what is its predecessor configuration, and that is just the Skolem function that expresses Y in terms of X. Okay, so this is a completely fun problem. Once again, we can do this as a synthesis problem. Other applications, similar applications where we reduce it to this kind of Skolem function synthesis are what are called conformant or conditional planning. So we have a set of states, we have some initial set of states, we have some goal set of states. These are defined symbolically as formulas. And we have a set of actions, non-deterministic actions that you can take in every state. And you want to know, does there exist a sequence of actions such that for all possible contingencies, for all possible initial states and non-deterministic choices that can come from the environment, you can execute this sequence of actions and reach the goal state. Okay, so this is really asking for a, does there exist a sequence of actions such that for all possible initial states and for all possible initial choices, there exists an execution that reaches the goal state. And once again, you would like to get the existentially quantified variables in terms of the universally quantified variables. So those become your Skolem functions. So, there are more optimized encodings like this, and then it really becomes a Skolem function synthesis problem. So once you have encoded your planning problem as a Skolem function synthesis problem, the Skolem function is the plan. It's telling you at this state, this is the action that you take. And the specification, the formula gives the, tells you logically what is it that you want to satisfy as you're taking actions from every state. Maybe you never want to get into a dangerous part of the, state space, so on, right? So, related to the question that Siddhartha had asked earlier, that we do indeed want to get the Skolem functions. Having them as black boxes is not good enough, because I want to have the plan to execute. And not only that, ideally, I would like to have a plan that is efficiently computable, compactly stored, and so on and so forth. But we are very far away from answering those questions. So synthesizing Skolem functions can give you, it is basically synthesizing the plans in these cases. Okay. So at this point, I would just like to put a laundry list of, several other applications. Cryptanalysis, as you have seen, we can do factorization through Skolem function synthesis. And if you can do it, cryptanalysis, there is use for that in cryptanalysis. Quantifier elimination, certifying quantified Boolean formula solvers, which has its use in lots of things. Reactive controller synthesis. So these are basically loopy programs that are sampling every so much time units and taking actions. This can also be reduced to Boolean functional synthesis once you have computed what is called the winning region, program synthesis, repair of circuits, a whole bunch of things. And not surprisingly, I mean, this problem has been actually looked at from a very, very, very long period of time. In fact, we found out that George Boole in 1847 actually looked at a version of this problem, which is called finding the most general Boolean unifiers, which is not exactly the Skolem function synthesis problem. Thoralf Skolem came up with the Skolem functions in 1920. So this was way, way before that. But George Boole did talk about a problem which is closely related to Skolem function synthesis. And there are, I will not even read out all of these names. There are lots and lots of techniques that people have used. I have highlighted in magenta a couple of techniques that I want to talk about a little bit because we have worked a little bit more in this. This last thing, as you can see, is exactly what we were seeing in action in flash fill, for example, that you do an intelligent guess or you do some learning for a Skolem function candidate, and then you check whether it is meeting your specification, the specification that you have inferred maybe from the data. And if not, then you repair. And this repair is incremental repair. And I will actually show you a demo of the tool which will do this. And there is this other approach which is called knowledge compilation, about which also I'll just talk at a very high level, which also allows us to synthesize Skolem functions. Basically, if you can represent the specification in a certain form, you can synthesize Skolem functions easily. So this is what is traditionally called in the AI literature as knowledge compilation. Okay, so now, before I get into how hard is Boolean function synthesis, I want to show a little demo for all of you. And this is a demo from our AAI 22 tutorial. Is my terminal visible, Arghya?
Yeah, we can see the terminal.
Right. Okay, so let me first show you some of the specifications. So we will start off with some ready-made specifications, and then we'll change it based on how we want me to change it, or some random changes we'll do, and we'll see what happens. Okay. So over here, I have a directory called SMT files, and here we have written down some specifications. So for example, let's look at, let's look at div4.smt2, and let's see what this is doing. Okay. So this is actually the specification as a logic formula using a particular format that is kind of the standard in this area. It is called the SMT format. And without discussing all nitty-gritties of it, what this is saying is that I'm using the bit vector logic. So I'm going to talk about operations on bit vectors. And it says that I want to synthesize a function out, which will take two 4-bit bit vectors, and it will output a 4-bit bit vector. So its output type is 4 bits, takes 2 arguments, which are 4 bits each. And the 2 inputs are 4-bit bit vectors. And this is a relation that I want it to satisfy. Okay. So I want the function out applied to int1 and int2 to give me the result of the integer division, because these are bit vectors. These are not real numbers or floating point numbers. The integer division of dividing int1 by int2. Now, and what I'm going to generate over here, so you might say that, oh, okay, I mean, if you want to generate a simple program out of this, it's so simple, just write out is equal to int1 / int2. But what I'm going to do here is I'm not going to generate a program, I'm going to generate a circuit. So now as a circuit, it's not immediately clear how I'm going to generate the integer division. Of course, it can be generated, we know, but it's not immediately clear how we're going to do it. And what we will see is that, as I change the specification, or as I look at specifications involving other kinds of things, the circuit generated will also change, and we will see what the circuit looks like And we will also simulate the circuit to see whether it's really doing what we asked it to do. Okay, so we'll start off with this. As you can imagine, this is doing division, which is not a very simple operation if I want to just synthesize a circuit. I mean, the synthesizer that I'm using here has no clue what division is. It's just saying, okay, here is a formula that you have. I mean, it has no clue how to synthesize a divider. It just says that here is a formula. I understand what this logical formula is, and I have to synthesize a circuit which does this. And the way it will do is it will first guess something, then it will check, it finds errors, then it will again repair it, guess, check, repair, and it will iterate. So it will take a few seconds. So we'll see the thing sort of hanging, because that's what I want to also, sort of convey, that these problems are not always very easy to solve. So we have a little script over here. So it's in the directory above. So Python. This is our tool is called Synthesis. And I'll show you what this Python script is doing so that there's no cheating happening under the covers. And then I will give the file that we just saw, so div4.smp2, and I will also ask it to call the simulator so that after it, so what this call simulator does is that after it synthesizes this circuit, it allows me to simulate that circuit. So now I can specify some given numbers, and it will generate what the output of that circuit is, and we can see whether it's really doing integer division. So here is, some not the best GUI, but it took the SMT formula that I showed you, it converted to some format, and then it is, figured out what the different, circuit input variable should be with respect to this format. And then, as I said, it takes a few seconds, but if we wait for a few seconds, yeah, there it is. So it has synthesized this function in 31 seconds. So that was quite some time. And it says that you can find the synthesized colon function over here. And it is now simulating this. So this is a simulator which is just simulating whatever it has generated, div4 colon.v. And these are the two inputs. So it's asking me to give two input values. These are 4-bit inputs. So the input bits are from 0 to 3. So let me just give, I don't know, maybe one of you can suggest something. Do you want to suggest any 4-bit number, 4-bit unsigned integer number, and we can see what happens. Any suggestions? So 4-bit unsigned integer will go from 0 to 3. Pardon me?
2, 3.
23 is not a 4-bit.
No, 2 and
2
3.
and 3, I believe.
2 and 3. Okay, let us see. 2 and 3. And it says that the circuit is evaluating to 0, which is, I guess, the integer division of 2 divided by 3. Let's flip it around and see what happens.
3 and 2.
It gives 1. Okay.
Mm-hmm.
So this is just simulating a circuit that has been generated. Okay. We know what specification we had given. We had asked it to do integer division. And we are kind of looking at this result and saying, aha, yes, it does look like it is doing the integer division. But, the synthesizer has no clue. And I'll show you what the synthesizer has synthesized. It's a big circuit that it has synthesized. But that's what it is doing. I can give here, let's give something which exactly divides maybe 8 divided by 2, and it gives 4.
No, but that is more than 3 bits, 4 bits.
No, 8 is 4 bits, right?
Okay,
1
8
and
is
3
4
zeros.
bits, yes.
So, we can give whatever, 12 divided by 8, maybe whatever it's supposed to give, it gives 1, and 12 divided by 6 maybe will be 2. So it looks like it's doing its job. Okay. Now let's see.
Can I point out something minor?
Yes.
So when you synthesized the circuit, if you go above like a few lines,
yes,
it was like 3 seconds, I believe, not 31. Although it felt like a little.
No, it is into 10 raised to 1.
into 10 raised. Oh, I see. Sorry, I did not notice that. Oh, that is 31 seconds. I was very curious. Is it like CPU time or wall time? Which one you are measuring?
This is the wall time. This is not the
I
CPU
see.
time. This is
Yeah,
wall time.
that was like it. Yeah, 31 seconds.
Right.
Yeah.
Right.
Yeah, please go ahead.
Yeah. So now I want to show you what this thing that it synthesized. Okay. So you can see that it said that find the synthesized colon function in this file diff_force bfss.v. Actually, let's go to there and let's do. So you see that this diff_force bfss.v just got generated. It looks like a large file. This is actually printing. It's a circuit, so it is printed it out in the Verilog format. But we will visualize it using another tool. So let's do the visualization. So I'm using this is a standard open source tool from Berkeley called ABC. So this can be used to read circuits and do all kinds of operations and then also visualize them. So I'm already in the SMT files directory. So I said before, and what was the name of the file? :bfss. Okay, :bfss.v. Okay, and then this is a command which basically does some optimization because the circuit is large. And then I'll just show you how the circuit looks like. It's not really in the circuit form, but it's showing you what are the functions that it has synthesized. So this notation is also called the Berkeley logic interchange format notation. Some of you may be familiar. So it is saying that there are 8 inputs that, and we also we have a file which tells us which input is what. So we can show that over here. So there is this diff_4 var map. So it says that the input 1 is 4 bits and V2, V4, V7, V10. So you see V2, V4, V7, V10, that's the first input. And the second one is V3, V13, V16, V18. So V3, V13, V16, V18 reordered to have the layout in a proper way. And the output is V43, V45, V47, V49. So that you have there. And this is actually telling you what is the function that it has synthesized. So this function takes in all the 8 things. So I think, if you can see over here that there will be 8 placeholders and then the value of the function. So it is somewhat like a truth table, but it has these don't care status. It's saying it doesn't matter what the first 4 things, what are the first 4 things they are here but if the last 4 things are 1, 0, 0, 1, then it is going to have a 0 on it. Okay, 1, 0, 0, 1, then it's going to have a 0 on it, and on this bit of the output. And so this is actually, so there are 8 Boolean inputs, so there are 2 raised to 8, 256 combinations. But as you can see, this is it has not really listed out 256 combinations because it has done some optimization. It's figured out that certain values it doesn't need to care, and it has only printed out those where the function is 0. In the other cases, the function is 1. In other cases, it might print out those where the function is 1. Whichever is shorter, it prints it out. So this is what the automated synthesis procedure has done. I can now, of course, take this and convert it to a program. I can synthesize a circuit out of it. And this thing came from that specification that we saw over there. This is where we started, diff4.smt2. This is the specification that we started off with, and this is where we ended up. Okay, and this we have simulated and we have seen it's doing the right things. It's actually doing the integer division. Okay, and we did not need to know anything about how to do division in hardware or how to, actually even, how to do the truncation. Nothing. I mean, we just said, I want to do integer division, and automatically this comes out. Now, let me show you, so.
Supratik, just one moment.
Yeah.
Now, in your program, you did not give any examples of this divided by this should result in this, did you?
I gave directly the specification as a formula. This is the formula.
Okay. You gave the specification.
Yes. So this is saying that the output, so this part is saying that the output as a function of int1 and int2 should be equal to, so this is the the Lisp-like notation. So it is the operator and the
It looks
operand.
so much like Lisp.
It is a Lisp-like notation. And I'm saying that the output function, the value of the output is a function of int1 and int2 should be the same as the whatever the integer division of int1 and int2.
And out is defined as division.
In this case, I have defined it directly as division. Okay, but the synthesizer had no clue about how to get a divider.
I understand. I understand.
Right. So let me show you another example.
Now, the circuit which you showed, that may be correct, but is it the most efficient? Is it the most compact?
Oh, no. So as I said, quality of the synthesized program or circuit is a completely open problem. So, I mean, for this, what we do is we generate the circuit, and because it's a circuit, we sort of can use some logic optimization tools to optimize it a little bit. If it is a program, we can use an optimizing compiler maybe to simplify that program a little bit. But to be able to automatically generate a circuit or a program that in a guaranteed way has some quality guarantees, that is a completely open problem. There is absolutely no work on that so far.
I have two questions. So first question is from Shoris. He's asking, using this output, how do you physically design the circuit? If you could basically say briefly, what is the next step from here?
How do you physically design a circuit? That's an excellent question. Actually, I mean, this tool that I was showing you, so let me convert it to a circuit, and let me show you what happens if I convert it to a circuit. So, where did it go? It's showing something else. Okay, let me read it again. So the circuit turns out to be quite large, okay. And so the circuit turns out to have 18,871 two-input AND gates. So this is kind of like a normalized form of the circuit. Only two-input AND gates and inverters are present. It has 8 inputs. 8 inputs, 4 outputs, and it has this. And if I try to display this circuit, it won't be able to display it because the rendering tool won't be able to draw this 18,000 gates. But precisely for this purpose, let me show you another one where the circuit is much smaller and you can actually see the circuit. So because the circuit was so large, therefore I just showed you the functionality of this circuit. So if I do this collapse, then it gets it back from the circuit to just the functionality, and it shows this functionality which I just showed. But let me show you how a real circuit looks like. So let me take up maybe a slightly simpler one, maybe max 4 3R per second. Okay. So this is another specification. Once again, we are saying that this specification is in the bit vector logic. And here I'm trying to generate a function which will take 3 4-bit bit vectors, and it will generate 1 4-bit bit vector as output. So these are the input and output data types. These are the 3 inputs. These are the data types over here. And what is the specification? What is the relation between the inputs and the outputs? I'm saying that so in this standard language called SMT, this is saying bit vector unsigned greater than equal. Okay, so once again in Lisp-like notation, it's saying that out as a bit vector should be greater than equal to, so the function out in terms of input 1, input 2, input 3, whatever out evaluates to as a function of input 1, input 2, input 3, should be greater than equal to input 1. Similarly, the function out should be greater than equal to input 2, and the function out should be greater than equal to input 3. And this OR constraint should be satisfied, that either the input 1 is equal to the function out applied to input 1, input 2, input 3, or the input 2 should be equal to this, or the input 3 is equal to this. So this specification, as you can see, it is not telling me how to generate. It's not telling me what out is as a function of the inputs. It's just telling me that out should be greater than equal to int1, out should be greater than equal to int2, out should be greater than equal to int3, and out should be either equal to int1 or equal to int2 or equal to int3. So it has to satisfy these 4 constraints, that it has to be greater than equal to int1, greater than equal to int2, greater than equal to int3, and this one constraint which is a disjunction of 3 constraints, saying it's either got to be equal to int1 or equal to int2 or equal to int3. So if I just put this formula, this is just a formula on bit vectors relating inputs and outputs, and let's see what the synthesis tool does. Okay, so we'll try the same thing again. So we will come back here, run our Python script. And we will, this time we will give this file, what was that, max 4.3 arc, and we will once again ask for the simulator to be called, and let us see what happens. And look, this just came out so fast. It came out in 0.675 seconds. Okay, and it is saying that it has generated this over there, and it is asking us to simulate it. So it takes 3 inputs, and remember what was our criterion, that the output should be greater than equal to each of the 3 inputs, and the output has to be equal to at least one of the 3 inputs. Okay, that was our specification. So let's just give again, we can give some 3-4 bit numbers, maybe I don't know, 5 and 15 and 7 maybe, or maybe let's give an even number, 8, and it says that the output is 15, and now we can go back and check, is 15 greater than equal to each of the 3 numbers? Indeed it is. And is 15 equal to one of the arguments? Indeed it is, right? So it has computed, so it has actually now synthesized a function which is guaranteed to meet the specification, starting from a completely logical description of how I wanted the output to be related to the inputs. Okay, let's try out some other values. Any suggestions from anybody? Yes?
These are not, the number of bits are not restricted here. Am I correct?
These are 4 bits again.
4 bits again. Oh, I see.
Yeah.
So something from 0 to 15, I believe. Am I correct?
We can even give repeated values, for example, because at
Right.
nowhere in the specification did we say that the number should not be repeated. So whatever we have given as the specification, it has synthesized that. So yeah, I mean, you can tell whatever numbers. If there are any suggestions.
13, 12, and 2.
13, 12, and 2. And it outputs 13, which is indeed greater than equal to each one of them, and it is also equal to one of them. Okay.
I believe this circuit should be smaller because the last one was.
Yes, exactly. So now I will be able to show you this circuit. Okay. So let me go to the LC thing and let me read this circuit now. So this will be it's already in assembly files. So what did it say? Max 4 3 args colon BFSS. So max 4 3 args colon BFSS. Okay, and let me again do this trash and let me print stats. This also seems to have quite
This
a few
many
gates.
number of gates. Wow.
Yeah, so I'm not sure if it will be able to print it out.
Are these NAND gates?
These are 2 input AND gates and NAND gates. Yes, basically just 2 input AND gates and inverters. Okay, so let us see. I mean, maybe I can try to. So these are some optimizations. Oh, okay. So that optimization is not here. So I can maybe try to. Not very familiar with this logic optimization thing. So okay, that's also not there. Okay, let me try to see what happens if I try to show it. It may not be able to show. Yeah, so it's just showing what we had earlier. because it says that the set has more than 500 nodes. So the dot file is not written. So what we will do is, okay, so we will maybe look at an even smaller thing that we can see, okay? And let's come out of this and let's see, I think there are even smaller things over here. So we can maybe look at max2. Max2.smt2. So this is saying that it should synthesize an output as a function of two inputs. Once again, oh, but these are 2-bit vectors, so I think certainly we should be able to see this. I thought we can, okay. I think we can even see, okay, let us see what happens. Maybe we can even go to higher bits over here. Let's see. And let me change this to 3 bits so that it becomes slightly interesting.
I think the insert is on.
Yeah. So, right, so these are 3 bits. My inputs are 3 bits. And what I want is, I want the output to be greater than equal to input 1. I want the output to be greater than equal to input 2. And just for the fun of it, maybe let me just say that the output should be, you know, instead of equal over here. So here I have said the output should be greater than equal to input 1 and the output should be greater than equal to input 2. And just for the fun of it, maybe let us see here if I say the same thing, saying that one of the inputs should also be greater than equal to the output. Okay. So actually we can keep it whatever. I mean, it doesn't care what the specification is. So here I've done something interesting. I have said that the output should be greater than equal to each of the inputs. That's what you know. This line is saying the output should be greater than equal to imp1. This line is saying the output should be greater than equal to imp2. And this line is saying that the imp1 should be greater than equal to out, or the imp2 should be greater than equal to out. So let us see what happens. Okay, so we have saved it, and then let's
can I ask you? So these are this is particularly the reason, because you know this is why you said this problem is not exactly data driven. It is data driven, but not entirely data driven.
Correct. Correct. Yeah, because I can change the relation between the inputs and the outputs, right? And I don't need to provide.
Isn't it true that the data is being driven by the functions which data has been created logically by the functions you have written over there? And
so
logic is being trained on that.
So it's actually the other way around. You know, instead of saying that from the formula, let us generate the data, and then from the data, let us try to synthesize the function. Because the problem that will happen there is that if your data types are large, for example, if I give integer data types, or even if I give 16-bit data types here, you'll have to generate a very large data set. And what you learn from there, I mean, for example, you have to learn with 0 error. For example, if the decision tree or whatever model you learn even gives you 1 error, that would be differing from the specification, because on that input, it would not be satisfying the specification. So what we want is, we want to learn, we want to synthesize a function that absolutely faithfully, provably meets the specification for all inputs. And if you want to go the data route, you will have to generate data for all the inputs, and then make sure that your, I mean, that would be one way to do it, and make sure that whatever you're learning makes no error on the entire data set. And
absolutely, that is correct what you said, because otherwise you can't prove that it satisfies the entire data set.
Exactly. So therefore, we don't generate the data from the formula. Rather, if you give some data, we try to infer a formula from there, And that formula is also available for the user to see. For example, in flash fill, you can see what string you want, and you can even guide it. You can say that, no, this part of the relation, I know it should be like this. And then it tries to synthesize a function straight away from there.
Is this true that in this example that we are performing, we are kind of starting from the from step 1.5 or step 2, something like that? Like in the example, some data points were given, and from that, the step 2 was to generate these relations, and from that we were going to the visualization.
So okay, so that's an interesting question. Let me actually go back to one of the slides where I said, yeah, I think this slide. So when you want to synthesize a system, when you want to design a system, there are multiple ways in which you can specify what the system should be doing. Data is just one way of doing that specification. I guess it's also a way that is in vogue these days because of the popularity of data-driven stuff. But that's just one of the ways in which you can write the specification. I mean, for example, for certain, if you want to synthesize a function that will go inside an autopilot software or in a control software for a nuclear reactor, which is controlling the rate at which the nuclear reaction happens, you don't want to risk whether you have generated all data or not, right? You want to come up with a formula and you want to say, this better be the relation between the inputs and the outputs. And you want your system to actually satisfy that relation no matter what.
Yep.
Okay, so the specification by logical relation is actually the intermediate step to go through if you don't already start from here. When you're doing things where, for example, safety critical things, where the cost of a wrong misclassification by the system is large. Actually, even in machine learning systems, for example, there are these unmanned drones, right? Unmanned aerial vehicles. There are unmanned self-driving cars. And of course, a lot of the algorithms that they learn, the machine learning algorithm, is data-driven. But there is also what is, I'm sure most of you are familiar, that there's also what's called neurosymbolic techniques. And this is the symbolic part of it, where you actually give a symbolic relation that you want to satisfy. And you better make sure that whatever your model you're creating, your neural network, trained neural network, or your program or your circuit, it does not violate what you have said over here, and it tries to match as much of the data that you've given.
Yeah.
Okay. So this is the part that I'm focusing on in this talk. But yes, the data also plays a role. And in this case, I'm saying from the data, we can try to infer something, and then the user has access to it and the user can correct it. But whatever we are going to synthesize will be from this very formally specified and very unambiguous specification that every input and every output should satisfy this.
I have another question from, sorry,
Yeah.
Go ahead, Professor.
Yes,
Go
sir.
ahead.
So specification by logical relation part, I can infer it as the domain and range for the y and x in this data.
That is just, yeah, I mean, you can say the domain should be, x should not vary between outside this range, y should not vary outside that range, but that does not relate the inputs and the outputs as strongly as if you specify a relation between them. Like, for example, I showed you this one, right? I mean, here, of course, the inputs and the outputs are all n-bit integers, but probably the input is a 2 n-bit integer, the outputs are n-bit integers. But just saying that they're n-bit integers does not tell me that I want y1 and y2 as factors of x. So how do I say that? Actually, you can try this problem on your own. Try to train a neural network which does factorization. You can easily generate as much data as you want, right? You just take two numbers, multiply it, you get a product, give that product as the input and the two numbers as the output, and try to train a neural network which does this. It's extremely hard. Because this is, we know that neural networks are universal computing machines if you, arrange them in a certain configuration. But the amount of training data that you need to get a neural network to be trained to do factorization exactly is unbelievably large. It's very easy to generate training data for this, right? But when I write it as a specification like this, I mean, the specification is so simple. I mean, I don't need to generate any training data. And I say, okay, generate the system. If you can generate the system, then I have a factorization program. I don't need to worry about it. It is going to do factorization for every input that can be factorized. And that's, of course, the reason that this problem is hard, because if we could do this easily, then, of course, crypto systems would be broken by now, right? So the point is, logical specifications are different from just specifying a finite amount of data. Unless you talk about a logical specification for finite data types, and the data examples, the training data or the data from which you want to learn the function covers every instantiation of those data types, of those variables. Unless you do that, logical formulas they say something more than just a limited amount of data. Right? I mean, this example is actually very illustrative. I mean, I have asked a lot of my machine learning colleagues that can you train a neural network which will do factorization? And inevitably it comes down to how much data do you want to feed to it. And, you know, I say that, well, generate as much data as you need. I mean, who's stopping you from generating data? It's very easy to generate training data for this kind of a specification. But then it's notoriously hard to just learn this thing, to learn this program or circuit only based on data. It's notoriously hard. Whereas we can do this. For example, in our experiments, the tool that we have designed, which is the tool that I'm running in the demo, we are actually able to synthesize this circuit for up to, I think, 24 bits. So we can take a 24-bit number. So we automatically synthesize a circuit which can take a 24-bit number. And I mean, of course, it will run for even larger, but then the running time exceeds the timeout that we have given. So we can take a 24-bit number and we can give you its two factors. For every 24-bit number which is non-prime, we can give you two non-trivial factors. And this is based on zero amount of data. I mean, if you imagine, 24 is perhaps not so large for training purposes. It is whatever, 16 million, but it would require 16 million data points. And even then, I would not know whether the neural network I have trained is going to give me the right value. I mean, even if I give all of the 16 million, saying that for this input, this is the output, this input, this is the output. I mean, at the end of the day, the loss function is not guaranteed to be zero when I train a neural network, right? I mean, otherwise I'll have to do overfitting. So even if I give all of the data and if I try to learn something using data-driven learning techniques, unless I do overfitting, I am still not guaranteed that for every input I'll actually get the right factors. But here I start off with a specification which looks as tiny as this, and I just feed it to the tool, and the tool infers a certain, it sort of guesses something, it checks, figures out where it has gone wrong, incrementally repairs it. And at every point it is so, I mean, when the tool stops, when it says that I have generated something, it actually has a proof that what it has generated is implementing exactly the specification. It's only at that point that it stops.
Right. Unfortunately, because time is the culprit, we cannot take any more questions. But the last question I want to ask from the chat, and after that, we want to go back to you, Professor. Kantimoy Dasgupta's question is that about the characterization of the study that you are presenting. Is this fundamentally different from simplifying an expression via Carnot map?
So once again, take this example. So I do not know what y1 and y2 are as functions of x. So what am I trying to simplify? Right? I mean, this specification does not tell me what y1 and y2 are as functions of x. So, I mean, what am I, how will I generate y1 and y2 as functions of x? If you try to draw the Carnot map of this Carnot map will have as its inputs x, y1 and y2, and it will tell you for this value of x, this value of y1, this value of y2, whether this specification is satisfied or not. So in fact, yeah, if you look at this where I said, so we have a formula which takes both the inputs and the outputs as arguments. So I can draw the Carnot map for phi, but that does not give me the Carnot map for y1 as a function of x1 to xn, or the Carnot map for ym as a function of x1 to xn. Right? So once you have synthesized the circuit, like what I was showing in the demo, once you have synthesized the circuit, then of course you can try to do all kinds of minimization. But to get the circuit in the first place, I think, maybe this example is something that if there is one example you want to carry back from this talk, I think it's this example, saying it's actually ridiculously simple to write down this specification, even as a Boolean formula on the individual bits. As I said, this is not more than order n squared size. But we still do not know today whether there exists a polynomial time circuit that computes the factors of a given number. This is not known today. We do not know. It's an open question. But the specification is no larger than order n squared. Right? So writing the specification, which just gives you a relation between the inputs and the outputs. As I said, if you want x to be the output and y1 and y2 to be the inputs, this is trivial. You just generate the output. Basically, if you flip the arrows, you generate the output as a multiplication of the inputs. But here, I have the same specification, but I have designated x as my input and y1 and y2 as my output. And now this becomes an extremely hard problem. I'm asking you to factorize. Right? And we know of no polynomial time or polynomial sized techniques to do factorization, integer factorization. But the specification is very simple to state. So from the Carnot map of this, we do not have a way to extract a Carnot map for y1 as a function of x and y2 as a function of x. Right? Okay, so I guess I have overshot my time, but I started around 7-8 minutes late. So
no, please take your time to wrap things up.
Right. So let me come back to this and let me just show you one circuit which I can hopefully show you over there. So let us see. So we'll have 523, synthesis, file, files. I think this should be, I think it was max2.smt2 and also later. And it has generated 0.02 seconds, and it's a 3-bit, so it is bit 0, 1, and 2. So, and remember the specification that we gave here was that the output should be greater than equal to both the inputs, and at least one of the inputs should be greater than equal to the output. So let's just give some 3-bit numbers. 3-bit numbers means 0 to 7, so maybe 4 and 5, and it generates 5. The output is indeed greater than equal to both of the inputs, and at least one of the inputs is greater than equal to the output. Right? We can give another number, maybe 3 and 6, and it generates 6. The output is indeed greater than equal to both the inputs. And
what happens if you give 7?
7, sure. 7 is 3 bits. So 7, and what is the other number?
Whatever. Because
3.
you won't find a number greater than 7.
No, but it is greater than equal to. That's what the specification says.
Oh, the specification is greater than equal to.
Yeah. So
you always get a solution.
So right. So it's a very good question. Suppose I actually we can try it out. Let's try it out. So instead of greater than equal to, let's make it greater than, and let's see what happens. Right. So max 2. So here, instead of saying that the output should be greater than equal to, let me just.
What if there is an uncertainty which can lie in that range of these two inputs?
Excellent question. So let's do that. Let's try it out. So I think it's called UGT, greater than. So this means that the output has to be strictly greater than both input 1 and input 2. And if we want to say that, So let's actually even have some uncertainty. Great. So what we will do is we will remove this OR, and we will say, so we are saying the output has to be strictly greater than both input 1 and input 2. And one of the inputs, I mean, we have to make sure that
Your
for some
brackets
inputs,
don't match.
actually, let's just see what happens if I just put the things, right? So I've commented this out. So I'm just saying the output has to be greater than equal to both input 1 and input 2. Right? Clearly, this has uncertainty. If I give 7, it would be interesting to see what happens. Let's take the specification, right? So I want to synthesize a 3-bit function of 2 3-bit inputs, and all I require is that the output should be greater than, strictly greater than both input 1 and input 2. Okay. So
And there are multiple answers.
So there are multiple answers, and in some cases there are no answers, right? So remember what we said earlier, that just like for the factorization case, that for inputs for which there are no answers, it does not matter what answer you give, because no matter what answer you give, the specification will be falsified. So it will give some answer, but just like for any other answer, it will falsify the specification. The given answer will also falsify the specification. But if there are multiple answers, it is free to synthesize a circuit which gives you one of those right answers. Okay, so let's try that out.
Will you do it deterministically or different times?
Yeah, I mean,
it
it will finally synthesize a deterministic program, so that every time you give the same input, it will give you the same output, right? But which one it has chosen, is it choosing the smallest one or not the smallest one? That depends on during the synthesis process as it is trying to repair.
So if you synthesize it multiple times, will you get different formulations?
Not in the current thing, because this is a deterministic synthesis algorithm, but there are randomized versions of it where you can actually get multiple implementations, multiple programs or circuits, all of which are correct. But if you run them different times, you actually get different things. The current one that I'm showing, it's a deterministic synthesis technique. So therefore, this will always give the same thing. So let's do that. max2.72 and call some later. And there it is. So it came out really fast. I'm
curious about something. As you said, these two terms, deterministic and randomized. Do we know, as a computing community, what is the optimal amount of work we need to do in order to do this synthesis? And do we have a comparison with these two things, deterministic and randomized?
Excellent question. Actually, the next couple of slides are about that.
I see.
I'll just finish this and go to that. It's not about deterministic versus randomized, but it's about the deterministic complexity. Yes. So in this case, I need to give a 3-bit input, and I want something to be strictly greater than that. Okay. So let us start with something modest, maybe 3 and 5, and it generates 6, which is strictly greater than both of them. Okay. What happens if I give 5 and 3? Because the inputs are now flipped. I'm not sure whether it will give you 6 or it will give you something else. Let's see. It still gives 6, well and good. What happens if I give 4 and 6?
4 and 3.
4 and 3, okay, sure. It gives 6. Okay.
Okay, not 5. Okay, interesting.
Not 5, because it is picking up, it has synthesized something which provably satisfies the specification. If you wanted it to satisfy something which will also be the smallest value or something, then you have to write that in your specification. Then it will synthesize something which is as
makes sense. Yep.
Right. But now let's try to give 7 and 2 maybe, right? So now I want the output to be strictly greater than both 7 and 2, but the output is also 3 bits, and we know that there is no number which is greater than 7 and also, right? And also can fit within 3 bits. Which means what? Which means that there is no value of the output that you can generate which will satisfy the specification for these given values of the inputs. So therefore, any value of the output is fine. This is a deterministic function. It will generate something. It has generated 5, right? And you go and ask, is 5 greater than or equal to 7? Not at all. Is 5 greater than or equal to 2? Not at all. So since the value that it has generated is not satisfying the specification, this also becomes a test that there is no value that will satisfy the specification. Because if there was even a single value that satisfied the specification, it will generate that. So for example, if I give 6 and 5, let us say, there is only one value that will satisfy the specification, one value which is represented in 3 bits and greater than both 6 and 5, and it will pick up that value, right? But if I give 2 and 7, then since there is no value, it will generate something because it's a circuit, it's a program. Given any input, it will generate an output, but that input, but that output will not satisfy the specification, right?
Yep.
And in this case, I think we will be able to see the, so let me restart this whole thing again.
Are you discussing how you validate what has been generated?
Yeah, I have slides for that. I just hope I'll be able to get there. Just give me a second, just a second.
This one should not take too many gates, I believe, this circuit.
Yeah, sorry about that. Yeah, this one I don't think will take that many gates. So let's start the PLC. And then let's read what is the thing that it generated. It's called max2:BFSS. So max2:BFSS.v. Let's trash it. And let's stats. Just 32 gates. We can actually see this now. So there it is. Okay, so this is not an optimized version of the circuit, but this is some version of the circuit. And here you can see that screen. Okay. So here you can see that there are 2 3-input gates here, and there is a constant input, which is basically saying that some bit can always be set to 1. This is very interesting. A particular bit, we can actually figure out which bit this is, can always be set to 1, and the other 2 bits are generated here. Each circle here is an AND gate. A dotted edge represents a connection with an inversion. A solid edge represents a connection without an inversion. So this is a circuit that you have, which has actually synthesized something which is strictly greater than each of its 2 inputs whenever it is possible to get such an output. Okay. So, and we can see here what are the so max2 bar max, right? So so the output has V7, V9, and V1. So this is the least significant to most significant. So it's basically saying that you can always set the most significant bit to 1, and which is true, right? I mean, if you give me any argument and if you want me to synthesize something which is always greater than both of them, why should I care about making the most significant bit anything other than 1? So we can go back and try to run this thing again and see it comes out. So suppose I give 0 and 0, it gives 6. See, the most significant bit is 1.
Yep.
Right? And if I give, maybe 4 and 4, it also gives 6 because the most significant bit is 1. So it has been able to figure out. So if I give 1 and 3, maybe.
By looking at 1 or 2 examples, that you could figure it out. That it will give
yeah. I mean, looking at 1 or 2 examples, you can figure it out. But remember, this circuit has been synthesized without looking at any examples, just from the specification. And it has been able to figure that out. But this is, as I said, one way of synthesizing the circuit. Okay, I mean, of course, the synthesizer that I'm showing you is a deterministic synthesizer. So if you give it the same specification, it will synthesize this every time. But we can also have, I mean, for example, if I gave 0 and 0, it was perfectly okay to say 1 over there and not 6. Okay. So that's, some kind of the demo that I wanted to show. Now, let me quickly get back. I know I'm holding up everybody, but let me quickly state some important results that we have. and I'll then wrap up. So maybe another 10 minutes I should be able to wrap up. Is that okay, Arghya?
Absolutely. This is such a driven discussion. Yeah.
Thank you. So, so how hard is this problem, right? I mean, we have seen for division, it took 31 seconds. The other things took quite fast. So how hard is it? So if we represent the specification as a Boolean circuit in negation normal form, and the Skolem functions, if we also want them as Boolean circuits in Skolem normal, in negation normal form. Negation normal form means the circuit is made up of only AND or gates. All negations are at the inputs. Then it's not very hard to show that this problem is NP hard, but actually it is much worse than that. In fact, we were able to show that, so in complexity theory, there is this thing called the polynomial hierarchy, which is an infinite hierarchy, and it's an open question whether this hierarchy collapses to any finite level. And we were able to show that unless this hierarchy collapses to the second level, there will always exist specifications for which the Skolem function sizes cannot be polynomial. They will be super polynomial in the size of the specification. And even worse, this is another complexity theory hypothesis, which is open, which we do not know whether it's true or false. It's called the non-uniform exponential time hypothesis. So unless this hypothesis fails, there will always exist specifications for which the Skolem function sizes are exponential. And I mean, if your Skolem function size is super polynomial, you will need time super polynomial because you'll at least have to write out that Skolem function. And if your Skolem function size is exponential, you will need exponential time. So, basically what this means is that efficient algorithms for Boolean functional synthesis are unlikely. And this is not because we are not being smart enough in coming up with the right algorithms, just because there are fundamental computational hurdles. So there was a very interesting question that was asked about what is the randomized complexity. We don't have a complete analysis of it so far. We have the analysis only for the deterministic case, but that's a very interesting question to follow up. Okay, so this is bad news, saying that this is an important problem, but we know for sure that we are unlikely to get efficient algorithms. And therefore, what do we do? But this is an important problem. So basically, we came up with these two ways. One is called this guess, check, repair approach. We guess smartly and efficiently. And there is a theory about how this guessing should be done. And then we check if the guess is correct. And this check actually reduces to checking whether a propositional formula is satisfiable or not. If you look at it very naively, it would amount to asking whether this QBF formula, we had this QBF formulation here, right? Yeah, it would amount to asking whether this quantified Boolean formula is true or not. But quantified Boolean formula satisfiability is much harder. It's p-space complete, whereas a propositional formula is NP complete. So it turns out that in this case, we don't need the quantified Boolean formula satisfiability. We can actually reduce the check to checking the satisfiability or unsatisfiability of a propositional formula. So we can use the power of modern satisfiability solvers. And then if the formula turns out to be unsatisfiable, we know that we are done. We have obtained a provably correct Skolem function. Otherwise, whatever satisfying assignment comes out from this check, that becomes a counterexample which tells us where did our guess go wrong, and we use that to guide the repair. So that's at a very high level what was happening in the tool that I showed you for the demo. It's doing smart guess, checking using a satisfiability solver, and then doing iterative incremental repair. And the other approach is, as I mentioned, it's a knowledge compilation approach where you take the specification and represent it in a certain form, you compile it to a certain form, and then we have theoretical guarantees that once you get it to that form, from that form you can get polynomial time synthesis, where the polynomial is in the size of that representation, of that special normal form representation. And this actually turned out to be very interesting because we were able to characterize efficient synthesis. And I have a little slide on that where I'll show you what do we mean by characterize, which means any specification that admits efficient synthesis has to be, in this nice normal form modulo some polynomial time transformations. And of course, this leads to the question of how do I take a given specification, like the specifications I was talking about, and how do I compile it to the special normal form? And so we have done some work on developing these compilers, knowledge compilers as they're called. So the guess, check, repair approach, quickly is this flow that I start with the specification. I quote unquote guess. So in fact, as I said, there is a theory behind how we do this guess. And in fact, we can use machine learning here also to do the guessing. Basically, we sample the specification, generate a certain set of data points, and from those data points, we learn some candidate scoring functions. That's one way of guessing. There is another way of guessing, which is basically looking at the structure of this formula and trying to infer something from the structure of the formula, find the candidate scoring functions. And once we have this candidate scoring functions, we do a check if this is the correct vector of scoring functions. And as I said, this check is one satisfiability check for a propositional formula. And if this check succeeds, which means the propositional formula turns out to be unsatisfiable, then we just output the scoring functions. If the check fails, which means the propositional formula was satisfiable, we take the satisfying assignment as a counter example, and we repair the candidate scoring functions, and then we iterate around this. And we have a progress guarantee here that every time I go around this loop, I'm coming one step closer to one set of correct scoring functions. So therefore, this loop cannot go on forever. It must terminate eventually. And that's a very high-level description of the guess, check, repair approach, which is the approach that you saw in action. The other approach, which is the knowledge compilation approach, is basically saying you take the formula in whatever form, maybe conjunctive normal form, maybe as a circuit, and then you have a compiler which translates this formula into a special form, which we call synthesis normal form. And then after that, there is a polynomial time algorithm which can just synthesize the scoring functions from here. And just to give you a very high-level idea of what this knowledge compilation business is, so those of you who are familiar with knowledge compilation in the artificial intelligence literature may recognize this form. It's called the decomposable negation normal form. This is used in probabilistic inference. So here what we say is that a given formula is represented as a circuit. Here are the leaves at the inputs of the circuit. It's basically a DAG. You have AND gates and OR gates in between. This is very old work, 20 years back. And this negation normal form, decomposable negation normal form, says that in this circuit, you never have these three kinds of situations. What is the first kind of situation? That you cannot have an AND gate whose two inputs eventually come back to the same, whatever variable you had over here. You cannot have an AND gate whose two inputs come to one of a variable and the negation of that variable. And you cannot have an AND gate whose two inputs eventually have a path to the negation of the same variable. So if you disallow these kinds of AND gates, and these are paths in the circuit, if you disallow these kinds of AND gates in the circuit, that circuit is said to be in decomposable negation normal form, has very nice properties useful for probabilistic inference. It turns out that and it's also the case that every Boolean formula can be written in this form. This is a universal normal form. Every Boolean formula can be written in this form. So if you take your specification and if you write it down in this form, if you compile it down to this form, it turns out that you can already do polynomial time and space synthesis from here. This is a sufficient condition for polynomial time and space synthesis. So this was, based on some normal form that was already existing in the literature. There are already, state-of-the-art compilers which will take an arbitrary Boolean circuit, compile it to this form. Once you get it down to this form, you can do synthesis easily from here. We went a step ahead from here. So, and what we said is that, those three kinds of things are not really necessary. In fact, you can just disallow one kind of thing, that an AND gate should not have a path to a variable and the negation of the variable. And that is sufficient for polynomial synthesis, polynomial time and space synthesis. And then we went further. We said that, okay, we can generalize this even more. And in the interest of time, I will not go into the specific technical details of it. But we said that we can generalize this even more. And even if this kind of condition is not satisfied structurally, as long as at the output of the circuit, I can't semantically get a variable and its negation, then basically a path that eventually comes from a variable and its negation semantically, not just structurally, even then that's a sufficient condition. And finally, we took it to the last possible limit, where we generalized that condition even further, and we came up with a normal form that is both a necessary and a sufficient condition for polynomial time and space synthesis, which basically means that if you have a specification and if you are hoping to get an efficient synthesis algorithm for that specification, it better be the case that that specification looks like this modulo some polynomial time transformations. You're allowed to do some polynomial time transformations, but beyond that, the specification should look like this, because this is both a necessary and sufficient condition. So this characterizes what is efficiently synthesizable. At least it provides one characterization based on the structure of the representation of the specification about what is efficiently synthesizable. So I'm not going into the technical details of this. These are there in our papers. And based on these, we have developed these two tools. So BFSS, as I was invoking during the demo, this is our tool that we call blazingly fast column synthesis. Well, the reason we call it blazingly fast is because either it's really blazingly fast or it's very, very slow. In the cases where it's very, very slow, it's basically going around that incremental repair process too many times. But this is currently among the best Boolean functional tools, functional synthesis tools available. And then we also have a knowledge compiler, which goes from a CNF representation of the specification to the special normal form, which we call the synthesis normal form. And currently, this is the only knowledge compiler available for synthesis. And to summarize, I would say that hopefully I have been able to convey to you that functional synthesis is a very fundamental problem, has a very wide-ranging set of applications. There is a long history of work that has sought to push the scalability envelope. Working from India particularly, we have been able to come up with two of the state-of-the-art techniques over here. So one is the guest check and repair, which is more like a paradigm. Others have also followed this paradigm subsequent to us, and the other is the knowledge compilation approach. And based on these, I just wanted to show that what's happening over the last few years, that in 2018, out of some 609 benchmarks that we put together, the best tools were able to solve 247, the best Boolean functional synthesis tools. And now that has been steadily increasing. And last year it was 509 solved. I'm sure this year it's going to increase more. So as you can see that, there's progress happening in the technology needed, in the theory needed to actually solve this problem. We had a how-to tutorial at AAA 2022. The challenges for the future, as I've been saying right from the beginning, and several of you have also pointed out, currently we do not have a good way of incorporating quality of synthesis into the final programs of functions that we are synthesizing. This is, I think, one very big challenge that needs to be done. For example, we would like to say that I want to synthesize a circuit of polynomial size so that I can evaluate every time in polynomial time. Every time I want to evaluate it, I take polynomial time. Or I might want to say that I want to get a circuit which is no larger than n cubed, where n is some size of the input. Now, or I want to get a program which is no larger than a certain size or doesn't use certain operations. So these quality metrics on the synthesized column functions, we have no good techniques right now. Beyond single functions, basically, where I can have a specification which talks about f of x plus f of y should be greater than x plus y. So it's the same function I'm using with different arguments. And, so now I need to generate this function in a way such that it's sort of, or I can say f of x plus f of minus x should be greater than maybe f of y plus f of minus y, something. So beyond single functions and beyond propositional logic, actually the as I said right at the beginning, once you start going into slightly richer logics, very soon you get hit with, for example, with integers. We already know that Skolem functions are uncomputable. So if I give you a formula on integers, unbounded integers, we can very easily show that there exist Skolem functions, but all of them are uncomputable, which means I cannot get a program or a Turing machine or a circuit or anything which will implement that function. So we have to then carve out small fragments, or rich enough fragments, useful enough fragments, and we have some work on that as well, where for certain fragments we are able to actually synthesize Skolem functions beyond propositional logic. And I'd like to end with this quote from Byron Cook, who heads the automated reasoning group at the Amazon AWS, Amazon Web Services. And I think he came up with a very interesting observation, which says that in this field of automated reasoning, there is a virtuous cycle where newer application areas drive more interest and investment in foundational tools, and improvements in foundational tools drive newer application areas, and this keeps going round and round, benefiting everybody. There are very nice theory problems, there are very nice foundational problems, there are very nice applied problems, and you end up solving real world problems. Of course, what I've showed today is far, far away from solving something like factorization, but these are steps that we are taking towards that holy grail, which is to be able to do automated synthesis. And this is just saying that, well, baby steps, but nevertheless we are moving forward. So with that, I'll end. I must apologize for overshooting the time that was given to me, but I'm happy to take any questions now, later, whenever.
Please do not apologize. It was our pleasure to host you. This was such an informative session, I would say. Thank you so much for your time, firstly. Because
Sure.
we know that we are comfortable asking for 2 hours from your precious time, and we were not comfortable asking for more. Thank you so much for giving us that time.
Yeah, thank you.
We had, I also want to add for today, we had a wonderful erudite audience today. Thank you so much for being here.
Yes,
Professor Sengupta, Professor Dasgupta, Shouris, you asked some really good questions.
Yes, it's always so much, gives so much of a better feeling when there is an interaction happening. Otherwise, these online sessions, I'm just speaking at a blank screen.
Right. Yep. Yeah. In most of the talks I have seen, like, if the windows are like, it is mostly black if you do not have the videos on or things like that. Right. So yeah, it's like demotivating at times.
Right.
Thank you so much for your time. If anyone wants to ask any questions, please.
I mean, my email address is my first name at iitb.ac.in. So if you have any questions, please feel free to shoot those questions later on as well. I may not have answers for everything, but whatever answers I have, I'll be happy to share.
This is take advantage of being in this fraternity. Shoot your questions to Professor Chakraborty. He encourages that. Thank you so much, Professor Chakraborty.
Okay,
in that case, we will wrap it up. Thank you so much, everyone.